Hello, welcome back to our organic lecture series on carboxylic acids. In our previous lectures, we talked about how we can name carboxylic acids and how we can form a carboxylic acid. Now let's look at some of the reactivities of our carboxylic acid and some reactions that we can do. So if we start with our structure of our carboxylic acid, we see we have a carbonyl directly attached to an OH group, right? Now normally when we did these reactions, we did nucleophilic substitution. With our carbonyl groups, we'd have a group attached and then something would kick off. So for our nucleophilic substitution reaction, if we talk about it, and we'll put L, we'll talk about that in a second. Nucleophilic attack, electrons come up. So we get addition of our nucleophile and L. As the electrons come back down, what happens to these groups here, right? What happens? We're actually going to then kick off our L. And we get addition of our nucleophile, and we lost L, right? L came off, right? What does L represent? What does L generally represent in this reaction? L is going to represent what? It's going to represent our leaving, right? L is going to represent our leaving group. So as we know, the better the leaving group, the more stable that leaving group is, as it comes off, the faster the reaction will be, right? So the reaction goes faster with a better leaving group. Reaction will go faster with a better leaving group. So our question is then, if we look at our carboxylic acid, is this carboxylic acid a good leaving group, right? Is this reaction going to go quick if we have an OH group here, right? What do we know? Well, we already know that we've seen OH groups here, right? Not a good leaving group. Right? It's not a good leaving group because, remember, the OH group gets kicked off, it's going to make an OH minus, right? And we know OH minus isn't very stable. It's pretty reactive because we use the OH minus multiple times to do lots of different reactions as a base and as a nucleophile, right? So our OH group here is not a good leaving group, as we know that. We've seen that before, right? So if we try to do nucleophilic substitution reactions with just a carboxylic acid, the reaction is not going to work too well, right? It's going to go very slow or not at all, right? Or we have to use a very, very strong reagent to make the reaction go, right? So what we need to think about is, what else can we use besides the OH group that can make this reaction go faster, that also be a good leaving group, right? And so if we look at the different types of leaving groups using the carboxylic acid derivatives, we have our amide, we have our OH, we talked about carboxylic acid. Here's our amide. Carboxylic acid that we know about. We have this group here, which is what? This is going to be our ester. Those functional groups are super important, right? We got to know those functional groups. Ester, and then we have our last one over here, which is this one. Right? Which is going to be that. And that's going to be what? Our acid chloride. Okay. So out of these groups here, which one do you think would be the best leaving group of all these ones? Our NH, our OH, our OR, and our Cl. Which one of these do you think is going to be the best leaving group? Which is normally the good leaving group? Which one have we maybe used before as leaving group? That we've seen as a leaving group, right? Which? And you're right. It's going to be our carboxylic acid. The chlorine is a good leaving group. Chloride. A good leaving group. Okay, so this is a good leaving group. That means then, if we go back to our first statement here, the reaction goes faster with a better leaving group, meaning that the reaction is going to be fastest for this acid chloride. This is the one that's going to give us the fastest reaction. It actually gives us the most reactivity as well, right? Because that good leaving group comes off. These ones, the reactivity is a little bit less, right? as we go through, and we'll talk about each one, right? So our acid chloride is going to be the best one to give us that reactivity in terms of being able to do nucleic substitution with our carboxylic acid derivative, right? Because carboxylic acid, we can convert carboxylic acid into a chloride, right? No problem. We can make the acid chloride, not a problem, okay? So we have to take that into consideration that this group is not a good leaving group. And as we look at the different derivatives of a carboxylic acid, NH2, OH, OR, and Cl, the reactivity is going to be different, the reagent is going to be different, the reaction is going to be different, right? That's what we'll look at. And so we'll focus on each one. We'll focus with the acid chloride first, and then we'll work our way through the esters, the carboxylic acid a little bit in the end, right? And as we go through, it'll be less reactions that we can do. We'll start with the carboxylic or the acid chloride because this is what we can do all types of reactions with, right? Now, while leaving this before we end with this video is how can we take a carboxylic acid and convert it into a acid chloride, right? How do we do that? So I'm going to place this over here and up here. And so I'll leave you with one reaction for how can we go from a carboxylic acid to an acid chloride? We're going to use SOCl. Right, this is our big reaction. So that's our reaction for this video here, is that I can take a carboxylic acid, react with SOCl2, and convert it to an acid chloride. Once we have our acid chloride, we'll go ahead and do some reactions in terms of what kind of reactions can we do with the acid chloride, right? A lot of these reactions are going to be substitution reactions in terms of that. While our nucleophile is going to attack the carbonyl, electrons come up, they come back down, they're going to kick off that chlorine, and we get a new group. Okay? So we'll go through those reactions, and then we'll go through the esters, the carboxylic acids, and the amides, and the different reactions that we can do, right, for formulas. All right? So our big reaction for today is carboxylic acid to acid chloride using SOCl2.